Tonight we are talking about one of the coolest things in the world, which is communication. And no, I'm not talking about going outside and talking to a real person. I'm talking about computer chips communicating with each other, which is way, way cooler, let's be honest. Today we're talking about the big three embedded wired protocols, those being I2C, SPI, and UART. If you're familiar with the embedded world at all, you've probably heard these terms thrown around. Tonight, hopefully, we'll be able to demystify those for you. We'll go over how each protocol works, the different wires that are associated with each ones, the advantages, the disadvantages, where you might want to use one or the other, because there's no definitive way to say, for example, SPI is better than I2C or UART is better than both. It's all situational, and when you're designing your embedded system, you really have to take all of the trade-offs into account. Sorry for the long wait on this one, by the way. I've been out in the surf, both literally and figuratively. Stick around if you want to see a video on Bluetooth Low Energy, because I'll be doing a completely separate one on that in the future. So we're going to start by looking at this document here from Analog. Now, in terms of resources for embedded systems, both Analog and Texas Instruments do great write-ups that you can just find on the internet about embedded concepts. They do require a little bit of knowledge about embedded concepts. So for example, here you can see they mention right off the bat ADCs, DACs, shift registers, SRAM. You're going to have to know what that kind of thing is. But if you're already reasonably familiar with embedded concepts, Analog and Texas Instruments, excellent resource, cannot recommend them more. One of the first things to note about SPI is that it is a master-slave paradigm. What do I mean when I say that? And the terminology gets a bit murky. Like online, you might see them referred to as main and sub, primary, secondary, things like that. I'm going to use the terms master and slave throughout this video for historical reasons. In textbooks and things, you'll likely see them referred to as this, but just be aware the terminology does change. What I mean when I say that is that you typically have one MCU or chip that is coordinating communication flow between multiple other chips or MCUs on the bus. So for example, you might have one MCU that is in charge of doing a whole lot of functions, and you might have other peripherals, like for example, they mentioned ADCs, DACs, shift registers, SRAM. These kinds of things are needing to send information to the MCU, and SPI and master-slave protocols essentially say, I've got this one MCU in the middle, and it's going to coordinate when all of those peripherals can send data to me. It also works the other way as well. If I need to send data to one of my chips on the bus, and let's pretend I'm a DAC, right? I'm a DAC and I'm receiving information on the bus. How do I know that I'm actually the one that's supposed to be receiving the information? And so a master will coordinate and tell the slave, you are the one that is intended to receive this information when it's being written to on the bus. And if we scroll down here on this document, they have what a typical SPI bus looks like. So here we've got the main over here, they call it in this document, with three subnodes, so this would be the master, and then these three are slaves, main, subnode, primary, this one, these are all secondaries, whatever terminology you want to use. So let's have a look at this bus here, and we'll explain all the wires that are in use. So I want you guys to ignore these two chips over here, and we're just going to consider this one, and these three lines here. So this is what we are talking about before, this CS pin. This stands for chip select or slave select, depending on the terminology being used. And this is how the slave knows that it's the one that's that is intended to be talked to. So for instance, on SPI, typically, all of these chip select pins will be in the idle state of high. And then if I want to talk to one slave in particular, I will set its select pin low. And then it knows that it's the one. So for example here, if I want to talk to node number 2 over here, I would set its chip select pin low, while these other two remain high. And so that way, all of the nodes know that, for instance, this one knows I'm not meant to be talked to, this one knows I'm not meant to be talked to, but this one in the middle says, yep, I'm the one who's being talked to. Now let's talk about the other three lines. We're doing a lot of talking. This is communication, guys. So these three lines here, we have SCLK. That is the clock signal. So SPI, when you're receiving it, it's not like UART, and we'll contrast it later. It needs a clock signal to synchronize data. So these two lines here, MOSI and MISO, MOSI stands for master out slave in, also main out secondary in, depending on the terminology, and MISO is the opposite, so master in slave out. So for instance, I'm just sending data here on this MOSI bus, right? And you'll notice that it's connected to all of these slaves over here. So every slave technically receives all the data that I ever send, but they ignore it if their chip select pin is not signaled correctly. And with MISO, it's the slave can send information back to the master. So think like an ADC, for instance. And a MOSI pin would be appropriate if you were using a DAC. So with a DAC, I'm sending it a signal that I want converted to analog, so I'd send it over MOSI. With an ADC, I typically want to read in analog information. And SCLK is the thing that actually synchronizes when each bit is going to be read or written. So we'll go and have a look at a timing diagram. Let me find one for you guys. There was this great one over here, and there's two more things that I want to talk about with SPI. So with SPI, and I think they show it right here. Yeah. So there's 4 SPI modes that peripherals can be put in. So let's talk about clock polarity and clock phase for a second. We come on over to this diagram here. This is from Wikimedia. You'll notice there is a C pole equals 0 and a C pole equals 1. So C pole stands for clock polarity. So essentially in this case, we just determine what the idle state of the clock is going to be. So with C pole set to 0, you can see that the clock idles low. And in C pole equals 1, you can see that the clock idles high. So when the clock changes, you can see here it goes from the idle state of low to the active state of high. And here you can see it goes from the idle state of high to the active state of low. And the chip select pin, as I mentioned before, usually is idle high and then goes low. And if we want to talk about clock phase, you can see what this means graphically. Essentially, you can see here that this graph here with C phase equal to 0 gets kind of shifted to the right a little bit. And the reason for that is, it's because if we take the first state change here, you can see that we start on the first state change with a sample if clock phase is set to 0. But if you move this first state change down to clock phase 1, you can see we shift. And essentially what shift means, we're just writing data here. So think about this for a moment. If we have clock polarity 0 and clock phase 0, let's look at the first state change. So from here, we're going from low to high. So this is a rising edge. And we move this down. If we have clock phase equal to 0, then on our first rising edge, we're going to sample a data because we're bang right in the middle of this bit. Then we look at our second state change here. So we're going from high to low. So this is a falling edge. And you can see if we move this down, this lines up with where we would shift data out. And this table right over here, if you look, we can see exactly what we've just seen. So clock polarity 0, clock phase 0. Data sampled on the rising edge and shifted out on the falling edge. So we'll go through the table and we'll try and map this graphically, because you can look at this table and you're like, oh yeah, sure, I kind of get it. But if you actually look and line it up with the timing diagram, it makes a lot more sense. So let's shift to clock polarity 1. So you can see here our first state change, we're going to keep using clock phase 0 for now. Our first state change is a high to a low. So this is a falling edge. So here you can see that we sample data on a falling edge and we shift data out on a rising edge. Let's double check that real quick. So clock polarity 1, clock phase 0, data sampled on the falling edge, shifted out on the rising edge. You can see we confirm it. So clock phase 1, clock polarity 0. We look at our first thing here, which is a rising edge. Move that down, you can see we shift data on a rising edge, and we sample data on a falling edge. And let's double check that. So clock polarity 0, clock phase 1, data sampled on falling edge, shifted out on rising edge. And our last one here would be clock polarity 1, clock phase equal to 1. You can see down here, our first change, we shift data out, which is a falling edge. And down here, you can see we've got a rising edge that lines up with where we sample. So those are the 4 SPI modes. Hopefully the graphical representation of them made it a little bit more clear. And now we're going to talk about some of the pros and cons of SPI and some of the trade-offs that you make if you choose to use it. So if we scroll down for a little bit here and we'll look at some setups of our bus. If you're really switched on, you will have noticed we need a separate pin for every slave we're going to have on the bus, because chip select is how we tell the slave, I want to talk to you. So down here, they have a whole bunch of different setups that go through, and typically you can use a GPIO pin as a chip select pin. There's some other tricks that you can use that are detailed in this article, but for really basic purposes, you'll have a different GPIO pin for each chip select pin. And this can get a little bit tricky if you are limited on GPIO pins or you need to use them for something else. So that's one of the trade-offs you make with SPI. It's you can really stack up all the lines that you're using very quickly. And this can be bad if you don't have that many GPIOs or if routing is going to be a problem on your circuit board. So, why would you use SPI then? Well, if you can manage that trade-off, it's actually pretty quick, especially compared to I2C. And it's got flexibility that you can build your own messaging layer on top of it in such a way that I2C generally doesn't have. And now this can be a benefit or a drawback to you if you want to build your own messaging layer or you have a need to build it, then the flexibility afforded by SPI is really good. If you don't really care to build your own messaging layer, I2C already comes with a pretty much pre-built framework of reading and writing to registers. So we'll jump into that next. And if you do want to design your own messaging layer protocol, I have a video that I'll show on screen right now. You can go and check it out. You can use that to design protocols for either web applications, talking over sockets on a network, or embedded applications. Now we're going to chat about I2C, or sometimes called I2C by those not in the know. It actually stands for Integrated Circuit. That's where the squared comes from, which is quite clever in my opinion. But I2C, so for this we're going to be using this document by TI, and as I mentioned before, Analog and TI, excellent resources for everything embedded. Now, it's similar to SPI in that it's a master-slave type protocol. So again, you have one MCU that is coordinating communication between all of the other chips on the bus. But it differs to SPI in one incredibly key factor. It only uses 2 wires for everything. The entire bus only uses 2 wires. What are those 2 wires, you ask? Well, they are SCL. Let me see if I can zoom in right here. SCL and SDA. So you can see here in this little graph, I don't know, is graph the right word? Diagram? Diagram's probably better. We've got these 2 lines coming from the MCU. We've got an SCL line and an SDA line. So like SPI, it has a clock line to synchronize data. So SCL is the clock line for I2C. SDA is the data line. So on I2C, it's serial like SPI. So when the SCL line is signaled appropriately, you'll either shift out or sample data. So, 2 lines. How on earth does it do this? When SPI, like how does this guy right over here know that I'm talking to him and not this guy right over here? Well, I2C is an addressed protocol. So every device has an address. So that means if I want to talk to this guy right over here and I know his address, it's going to be different from this one over here. Now, there have been cases of I2C address collisions. I think the address is 7 bits from memory. I will correct that if not. But, and I'll put the number up on screen of how many possibilities there are. I can't remember off the top of my head. But you do get collisions from time to time. And so the address is usually baked in from firmware or on the factory level in the hardware. And some devices will have multiple you can choose between to avoid collisions. And I think there's I3C, which has a bigger address line. I'll put the numbers up on screen just to avoid collisions between addresses. But anyway, addresses, whatever, blah, 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 blah. There's quite a lot more to I2C, so let's go and have a look at an example transaction. Now, there's quite a lot more baked into the protocol than SPI. In fact, it actually has a protocol, messaging protocol, unlike SPI. So what have we got here? There's a start condition, there's a stop condition at the end, there's acknowledgements, there's read and write bits. So let's consider this write transaction. So I'm the master and I want to write to a particular slave. You can see here the gray is where the master is talking and the white is where the slave is talking. So to start us off, the master gives the start bit and then, 7 bits, the slave address. So that way, if I'm talking to all these guys up here, if I can scroll up, the first thing that I say is the address of the slave that I want to talk to. So if I'm the LED blinkers over here and the master is talking to the LCD driver, I'll see that for this particular transaction, it's not my address. So I'm just going to ignore whatever I get. So we'll scroll back down and you'll notice here, I mentioned before, there's a register as part of this. So before we do this, we send the slave address with the start condition. Then there's a read-write condition. So what that means, 0 is for writing and a 1 is for reading. So if I want to write to this slave, I send the write condition after its address, and the slave then sends back an acknowledgement. Then I send the register address of the register on the slave that I want to write to. So in the datasheet for my slave, it will have the registers that it exposes over I2C that I can write to, what they all do. So if I've got an I2C DAC, for instance, it might have an output register that I can just write to. And so I write the address here, and then I get an ACK, and then I send the data to that register, and then I get an ACK, and then I say stop. So that's a write transaction right there. And you can see here, because of the way that I2C works with this address, there's a lot more overhead to the protocol than SPI, but this is how it can get away with only using 2 lines. And we'll talk a bit more about that later on. We go and have a look at a read request. Now, a read request is a little bit more dicey. So if I want to read from a register on my slave, the first thing you'll notice, as I say before, is this thing right here. So we give it the start condition with the address, and we still have this read write set to 0 as a write, which is interesting. The slave then sends an ACK of its address. So basically, all this does is say, hey, I want to talk to you. Then we get an acknowledgement. It's like, hey, okay, you're talking to me. What's up? Then I send the register address like normal. The slave sends back the ACK. Then I'm going to send the address of the slave again, this time with a read condition. So I've sent the address of the register. I get an ACK. Now I send the address of the slave again with a read condition saying, okay, I'm going to read the data. And then the slave will respond with an ACK and the data from that register. Quite a bit to it, But this is one of the things that makes I2C so powerful. So you can see here that unlike SPI, where we kind of have to make our own messaging layer, there already is a sort of messaging layer in I2C. Now, I just want to make a quick note here about writing. So you'll notice here we specify the register address, but this is not actually always the case. And I think TI note this up here as well. It's common to have registers in I2C slaves. Not all of them will have registers. Some only have 1 register. So in the case where a slave only has 1 register, we completely skip sending the address in the first place because it's superfluous, right? It's only got 1 register. So instead you shift this data byte back here in place of the register address, and you just send the stop immediately. So it would be slave address, data byte to register, and then stop, rather than this 3-component transaction. Why would you want to use I2C? What are the benefits and drawbacks? Now, the obvious main benefit to I2C is the fact that you only use 2 lines and you can talk to, within reason, as many slaves as you want. Now, this is in direct contrast to SPI, where you need to use an additional chip select line for every slave. So if GPIO usage you need to be concerned about, or if PCB routing is going to be a drama, then I2C, it's a great solution. So in fact, if your MCU has I2C hardware built in, you don't really need to use any GPIO at all. You can just use the inbuilt I2C hardware. So why would you not want to use I2C then? Like, it sounds fantastic. Well, it's actually kind of slow. So you'll notice here there's a lot more baked into the protocol, and there's acknowledgements that need to be sent. It's a courtship type thing, like it's an entire transaction. It's a big deal. So naturally, rather than SPI, you just boom, 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 data. There's a whole process we have to go here, and that inherently makes it slower. It's going to be slower. So if speed isn't a massive concern for you, and you're concerned about GPIO, or you want this framework, like as I mentioned before, this has a framework, a messaging framework built in that's pretty well defined. Whereas with SPI, it's flexible in that you can build your own messaging layer, but that's also a drawback if you can't be bothered. If you want to see a cool real-world example of I2C in use, in this video right here, I went over the reverse engineering process of the RGB LED controller on my Gigabyte graphics card, which actually exposes itself to the operating system through I2C. So if you want to see me, and here I am as a young spring chicken with a much better haircut. I've got a kind of surfer dude haircut at the moment, but from 3 months ago, March 21st, that was a good day. That was a good day. I remember that day. But I'm explaining the background to this project where I reverse engineer the I2C communications with my Gigabyte graphics card. So check that out if you're so inclined. Now, the last of the big three embedded protocols is UART. Now, UART is also very popular, but it has one very key difference to SPI and I2C, and that's that it's technically not a master-slave paradigm protocol. So what I mean by that is essentially it's in the name. Universal asynchronous receiver transmitter. Both chips can send and receive at the same time of their own volition. There's no sort of master-slave coordination going on there. So let's have a look at this. And the reason it can do that is because it uses these two lines right here. It has a transmit line and a receive line. And naturally, if we've got two chips right here, the receive line of this one is wired to the transmit line of this one, and vice versa. The transmit line of this one is wired to the receive line of this one. Now you'll notice we're only really considering two MCUs here. Why is that? Why can't we use multiple like with I2C and SPI? Well, the reason for that is, let's say I want to add another chip into this, and I wire up the transmission line of this one to the receive line of that other chip. And so the receive line is shared between this one and this new chip down here that we're just randomly adding. That's fine. Both of them will receive it perfectly. But if I try and do the same thing and I connect up the transmission line to this other one, I'm going to have a bad time because there's going to be a lot of congestion on that transmission line. So with UART, we typically only really consider two MCUs. Because remember, this other chip can start talking whenever it wants. So there's no master-slave synchronization there. So typically we only use two MCUs. Now, important things to note about UART. We scroll down right here, we'll have a look at this data transmission packet. So what we have is a start bit, we've got a data frame, we've got an optional parity bit, and then a stop set of stop bits. So the start bit, we need to tell the other MCU that we're going to start a transmission. So typically you have a high line that goes to low, and then you immediately follow that up. So it's idle high, and then immediately follow that up with the data frame. And here, a parity bit. So if you're not familiar with what a parity bit is, let's say I've got this data frame right here, and it's a sample of bits, so 1, 0, 1, 1, 0, blah, 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 blah. The parity bit is used for error detection. So simply, a parity bit is one of the most simple forms of error detection around. You just count up the number of ones, and if it's even parity, you set the parity bit to 1. If it's odd parity, you set it to 0. There's different interpretations of it, like it can be the opposite, but essentially you're counting the number of ones to see if it's even or odd. So a parity bit is not a great error detection method for multiple reasons, but it's very simple, so it can get a lot of the low-hanging fruit. And we'll talk a little bit about error detection later on, because it applies to both UART and SPI. If you're switched on, you'll have noticed one really key thing, and that's the fact that there is no clock line in UART. How do we get away with this? How do each MCU, because remember we're transmitting asynchronously, how do they know when to actually sample the information the other is sending? And this is the case because of a baud rate. So a baud rate is essentially a pre-agreed upon rate of transmission of the information. So essentially, when I'm programming UART on both of my MCUs, I will choose a baud rate that they transmit data at, and so they both know to sample at exactly that rate. The most typical ones, as we're talking about here in this article, are 4800, 9600, 19200, 57,600, and 11,5200. Typically, I've seen 9600 and 11,5200 used really frequently. The other ones are still common, but slightly less from what I've seen so far. And one important thing to note about UART, by the way, is it's used very popular for like doing debug stuff. So for instance, you can find like UART to USB converters pretty much all over the place. And what that'll do for you is that you'll have a UART communication that shows up as a COM serial port on a Windows machine or a TTY on a Linux box that you can then get your MCU to send debug information to, or you can write data to the MCU while you're testing things. It's really, really useful, and you can do that all from a regular PC. But anyway, so baud rate, yeah, that's essential for each MCU to know when to actually sample the information the other is sending. And it's just predetermined, you program it in. And to calc that, calc is short for calculator, by the way, I'm just using slang. You use one of these formulas here. This is specifically for an AVR, but for most MCUs, it's pretty similar. I just check the datasheet to make sure that you're doing it right and to know what register you set. But for an AVR, for instance, here you can see the register that you set in order to determine the baud rate. It's calculated relevant to the frequency of the chip, obviously, because the baud rate is a predetermined bits per second time. So how do you actually know that? Well, it's relative to the frequency of your MCU. So here you've got the frequency divided by 16 times the baud rate. So if I had an 8 megahertz MCU, this would be like 8 million divided by 16 times 9600 if I was using a 9600 baud rate. And this is for normal mode, but you can also have double speed where you just do it by 8 instead. So then you would set this register as whatever the value of this formula turns out to be. And so in this case, you would be using that baud rate for your UART transmissions. Again, make sure you check the MCU datasheet to make sure you're doing that right. Choosing a baud rate is not just random fun and games. And I want to turn your attention to this very illuminating website to illustrate a particular point. So with sending more information faster, you would choose a higher bit rate, which means a higher baud rate. So if you have a look at this here, you can see this is a table of error rates of different baud rates at different frequencies on an AVR. So for instance, over here at 32,000 hertz, it's horrible across the board. You want to use any of these baud rates. If you scroll down to some of the more typical MCU for an AVR, you could see 8 megahertz here. We've got error rates of very low if you use these baud rates. But then as the baud rates get faster, so these ones here, your error rate gets a bit higher, and so on and so forth. So if you're using, for example, a 20 megahertz crystal oscillator, you can use that to get lower error rates on higher baud rates. And the same thing back here. Another one very common for AVRs is 1 megahertz, but if you're running your AVR at 1 megahertz, you can only really get 4800 at any good error rate. So it's a bit of a mix and match here. You can see at 3.6 megahertz, you actually get really great across the board. So determine what speed you're running your MCU at and then choose a baud rate appropriate for that. Or you could choose a baud rate and then find an oscillator that runs at the frequency that gives you a low error rate. Now this is just for an AVR. I'm not sure if it's the same for other MCUs, so just double check for whatever you're using, because in embedded systems, one thing is for certain, and that's that nothing is for certain. So your mileage may vary on this one. Benefits and drawbacks of UART. So with UART, if you've only got 2 MCUs that need to talk, or you need to use it for debug, as I mentioned before, it's great for debug, then you don't need to bother with all of the extra lines associated with SPI or the inherent overhead with I2C. You can just do this. It's flexible in the same way as SPI, that you can build your own messaging layer on top, and you could even include something like CRC or checksums to detect errors better than a parity bit. So guys, I really hope that this was useful for you. I hope it gave you an overview of the big 3 wired embedded protocols, so that you can understand the trade-offs in your own designs and know what they're used for, what you deal with when you choose one of those. And yeah, I really hope you enjoyed it. So let me know what you thought in the comments. Cheers.